when they met, we got something bigger than what we started with. So when they met, we got something bigger than what we started with. So this is the constructive interference. And when we said opposite, when they met, assuming they had the same amplitude, they basically canceled each other out. Destructive interference. So what I did, I wanted to somehow demonstrate this. I took two frequencies here that are just, obviously it's got some water damage, but two frequencies here that are just a little bit off. I took the blue one here and just traced it onto this clear plastic. Down. And so hopefully you can see that I've got one set of lines here that they're perfectly in sync with each other. And if you need me to bring it closer, I'd be glad to. I know not everyone's eyesight is as good as mine. Now, on the surface, you can tell that these are slightly different in the fact that even though they both start at 0, 0, this one ends on the way down, and this one ends just after hitting the bottom. So they are slightly different. If I put this into the transparency, line up the beginnings, and hopefully you can see now that although they start out together, the peaks are very close to each other. As we go farther on, the peaks get a little bit farther off. And then you can add the waves. You can just add them straight up. If they each peak at 1 and they peak in the exact same place, that should get an amplitude of 2. If one has an amplitude of 1 and the other one has an amplitude of -1, they should add up and give me 0. So if I add them up, I would get this. So hopefully you can start to see that the amplitude, the overall amplitude, starts to drop off. If I extend that, I get this. So this is where it's loudest, and then it fades off, and then it'll start getting louder again. So that's why you got that wow, wow. So it's the wow and the and make sure there's one other thing that or there wasn't one other thing that I wanted to hit. We did, wavelength. So as this is moving along, the distance from basically the length of a wave is known as the wavelength. It can also be described as the distance. It is a length. The distance a wave travels in one period. So if I'm starting at the peak, I'm going to end at the peak. If I start at the trough, I'm going to end at the trough. If I start at this point on the way down, then I'm going to go until I get to that point on the way down. If it's a steady wave, if it's a single frequency, then all those distances would be the same. Symbols and units. Symbol for wavelength is the lambda, lowercase lambda. It almost looks like a tau that's fallen over. Tau, and then if it falls over, lambda. that is wavelength. And what would be the standard unit for wavelength? It is a length.
Meter.
Oh, we just said it?
Meter.
Yes, meters. So I can write that in shorthand notation as in the brackets around it. The standard international wavelength, unit of wavelength is meters. Or for frequency, that's the hertz. It is a capital H, lowercase z. For amplitude, that depends. If we're talking about pressure, as with sound, then the units would be pascals. If we're talking about loudness, that would be decibels, or bells, actually. If we're talking about physically this long coil here, it'd be meters. And see, oh, and period. What would be the international standard units for period?
Seconds. Seconds.
Okay.
Dr. Fox, what was the meaning for SI?
Standard International. If anyone's got a better French accent, now's the time to say it. Okay, or international standard. So I've got this distance equals rate times time, or distance is speed times time. We're assuming that the speed doesn't change. So if we're talking about the time of one period, then the distance it travels is the wavelength. So however fast it's going, it is the wavelength. Wavelength is equal to the speed times the period. If I solve for v, that becomes the wavelength divided by the period. So if I said the wavelength was 5 meters and the period was 1 second, well, the wave has to be traveling at 5 meters per second. As I mentioned out there, frequency and period are reciprocals of each other, so that's lambda times 1 over the period, which is just lambda times the frequency. And so we have this other formula. I'm just going to flip the order around. Frequency times the wavelength. So if I'm looking at a book which uses nu for frequency, the nu for frequency, I have to find this equation to know what their nu looks like versus their v. Because it is really a pain in the butt. So if I'm using the nu, this is what it would look like. Yep. Times frequency times wavelength. Except in some fonts, it does get that confusing about which ones are V's and which ones are Nus. It really depends on the font that they're using. And the only reason I bring this up is not to confuse you. I'm not going to quiz you on this. It's just that if you run across it, my first year here, there was a student doing the nanotech program, was really confused about why they had speed in certain equations. And I looked at it and realized it wasn't a V, it was a nu. And so it is something that occasionally you might run across. And hopefully we will never talk about that again. Sushil.
What's the A stand for?
Amplitude.
Amplitude. And what does it say as the units?
What is that? It depends.
Okay.
The amplitude depends on what you're actually talking about.
Okay.
All right. Questions? sat down to the lab room to do our last lab.